Okay, so
Okay.
yes, it's again a pleasure to introduce the last speaker of this week, Adam Smith, and he's going to present topology on quantum computers. So,
Brilliant. Thank you very much. Yeah, thanks a lot to the organizers for inviting me, and especially to allowing me to present this online. It's a real shame that I couldn't be there in person. Yeah, so today I'd like to talk about some of our work with the Google team and with the theory team in Munich on realizing topological order using quantum computers. So it's a little bit of a shift from the last few talks on variational algorithms. Here we're going to be doing something based on exact topologically ordered systems. Okay, so let me start by thanking my collaborators. So we have the theory team at the Technical University in Munich, which is Leo, Frank, and Mikhail. We have our collaborators at Google who actually did the experiments that I'm going to show you. So that's Kevin and Pedram. On the extensions that I'll show at the end, also had Kirill involved, and also helping on the theory/experiment side, we had Christina, who is now at Microsoft. Okay, so let me start by giving a little bit of a spiel about topological phases and why we care about these. And just to clarify something I've not put on this slide is what I'm interested in are topologically ordered phases. So this is not including symmetry protected topological phases or topological band structures. I'm really thinking about 2D systems with intrinsic topological order. And a few reasons why these are interesting: they do not have local ordering in the way that we think about normal phases and phase transitions. They are not fully classified, even on a mathematical level. There's no general solution for these things. There's no general model for them. And then more practically, why we care about these is they have interesting exotic features, including anionic excitations for these 2D systems. So this means that we can have particle-like excitations that are not the normal bosons or fermions that exist in nature. A few other reasons is this idea of topological ground state degeneracies and the connected idea of topological protection. So if you put these systems on, with different boundary conditions, say on the torus, then we can get robust ground state degeneracies that are protected from any local perturbations. And this feature makes these systems useful for potential error correction methods and quantum memories. So these are ways that we can robustly store quantum information that is protected against local noise. And finally, just a comment that maybe a bit more ambitious would be actually using such systems for topological quantum computation. So by, as this nice picture on the right shows, if we start grabbing these anionic excitations and doing a complicated braid, then this is another way that we can actually do quantum computations that is protected against noise. Okay, so this, from a theorist, this is enough, but you might want a bit more. And a good reason to be interested in this is there's a lot of interesting experiments recently that have demonstrated that these might actually exist in nature, or well, more precisely in experiments. So the first example is in what's called Kitaev quantum spin liquids, or at least candidate materials for these. So one example is this ruthenium chloride, which has an effective 2D hexagonal structure, which is supposed to be described by this Kitaev model. And by looking at the quantized thermal Hall conductance, they find a value which is a half, whereas we would expect a value of 1 if we had fermions hopping, or itinerant fermions in the model. This value of a half signals that we have itinerant Majorana fermions in this model. So this is a signature of these anionic degrees of freedom. Maybe more direct experiment, well, it's still a bit indirect, is this anion collider experiment that was done a couple of years ago. So here they have a fractional quantum Hall system where they bring the edge modes very close together using this quantum point contact, and essentially they collide these edge modes. And by fitting with experiment, they find it matches with this thing. In this case, it's a charge 1/3 particle in the model, which is a fractionalized electron. And then the final example I'm going to give is a work that was done in parallel with ours. And sorry, the reference is not up to date. This is now published. In Rydberg atom arrays, they realized a very large topologically ordered system, which is actually in the toric code phase, which is related to what I'm going to talk about. And here, really, what you should look at is this kind of red curve. For the right parameters in their model, they essentially have this, this resonating valence bond liquid. So they have these dimers on this Kagame lattice, and the ground state is essentially an equal weight superposition of all of these dimer coverings. Okay. So the second half of my title, and like the point of this week, is that we want to use quantum computers to study these systems. And as I'm sure you're aware, we're now entering what has been coined this noisy intermediate scale quantum era. So this means that we have quite a large number of qubits now. It's getting to, you know, what is difficult to simulate potentially. We've got 50 plus qubits. We've got potentially hundreds of layers of gates. But these systems are still plagued by a lot of noise. And there's also a range of leading technologies. It's not just one. It's not just a one-horse race. We have superconducting qubits, such as IBM and Google's efforts. We have trapped ions, such as IonQ. We have photonic systems, such as Xanadu, silicon, such as Intel. So there really are a lot of companies and universities in the world looking at different technologies to realize these systems. And so it's natural to ask, you know, are they useful now or in a few years or long in the future? Okay, so let me be a bit more concrete about what I want to talk about the topologically ordered system I'm talking about. This is the Toric code, which may or may not be familiar, but this is essentially the simplest case of 2D topological order. It is defined on this square lattice. So we have spin half degrees of freedom, or qubits, that live on the bonds of this square lattice, which are illustrated by these white crosses. And the Hamiltonian has two terms. They have star terms, which are these A's. This is essentially a Z coupling between all spins that meet at a vertex, or star. And we have the plaquette terms. So these are a part of Pauli X operators around the square plaquettes of the lattice. Okay. Now, this system has a Z2 type of topological order. It has long-range entanglement. I'll talk about all of these things a bit later. And it happens to host these anionic excitations. So we actually have two types, or three, depending on your taste. We have the electric excitation, the magnetic excitation, and we can also think of like an electric and a magnetic together as another type of excitation. Now, it turns out that E and M both look like bosons if you think of them separately, but when we can combine them into E and M, this combined, this has fermionic statistics. So that's just a taste of, you know, the weird statistics of these anions, which I'll come back to. And another reason why this is such an interesting model, besides being the simplest example, is probably one of the most useful, most directly useful examples of topological order. And it's one of the leading designs for a surface code used for quantum error correction. Okay. So that's kind of like an introduction, setting the scene. Now just a quick outline of what I want to talk about for the rest of the talk. I'm going to tell you about the efficient quantum circuit that we designed to realize the ground state of this toric code Hamiltonian. Then going to talk about the experiments we did on extracting what's called the topological entanglement entropy. So this is like a signature of this long-range entanglement that these topologically ordered systems have. Then going to look at extracting the non-trivial anion braiding statistics, so showing that these particles don't just behave like bosons and fermions. Next, we'll talk a little bit about how this system can be used as a surface code for error correction. And we do a kind of passive error correction, which is kind of a stepping stone to the full-blown error correction. And then finally, I'm going to talk a bit about a generalization to basically use all of this formalism that I talk about in the toric code, but applied to a more general set of states, which are called string net states, which include a particularly interesting type of topological order, which is non-abelian. And I'll come back to that. Okay. Great. Right, so let's start with how to construct this ground state. So to construct this ground state, we have to realize a nice fact about this Hamiltonian. These two terms, this A and the B, they actually commute with themselves and with each other. So, I mean, you can convince yourself if you ever have like the overlap of these two terms, you'll only have an even number of operators, and so you can show that these commute. And so every term in the Hamiltonian commutes. And this makes it particularly easy to figure out what the ground state is. The ground state must have that the expectation of all of the star operators is 1, and the expectation value of all of the plaquette operators is 1. Okay. So to construct the ground state, what we do is we start from a state which has all of the AS equal to 1, and this is just the zero product state. This is just the state that the quantum computer comes in automatically. This already has this AS is equal to 1. Then what we do is we apply a projector onto this that forces you to be in the sector that all of the BP are equal to 1. Okay, and that's how we get the ground state on paper. And now what we have to do is convert this into a quantum circuit. So I've probably done this in the wrong order, but let me explain, what these pictures are. They look quite different to what I drew for the toric code on the other page. So let me skip ahead one slide to tell you how to convert these. So we have this black square lattice in the background. We have the spins on the bonds. And now what we do is we essentially can draw it like a skewed square lattice instead. And now if the stars are satisfied, then they will show up as blue in this, what we call a stained glass plot. And if the plaquette operators are satisfied, they'll show up as purple in this stained glass plot. If they're not satisfied, they'll both show up as kind of a gray white color. Okay, so let's go through the sequence that we came up with to implement this on the quantum computer. So what we start with is just the zero product state of Google's quantum processor. This is the Sycamore processor, or a subset of it of 31 qubits. And this initial state of all zeros, this has the star operators, the A's, satisfied. So these all show up as blue, but the plaquette operators are not satisfied. The expectation value of them starts as 0. Okay, so now what we do is we apply a sequence first of single qubit gates, and then 5 layers of entangling gates. And in this process, what we end up with is, this guy at the bottom right, where we have all of these satisfied. Maybe one way to understand this is that we in a Z basis, we want loops around each of these plaquettes, and you want a superposition of all of the possible loops. So what we do is we start with this with these Hadamard gates. This is essentially giving us this superposition but so far we've just placed it on the qubits. Now, by applying these CNOT gates, these entangling gates, we take it from just being single qubits, which are in superpositions, to actually generating these kind of loop configurations. I just mentioned that because if you're familiar with the Toric code, this loop configuration language might be familiar. But the important thing here is that it's very shallow. So we have 31 qubits, and with one layer of single qubit gates, 5 layers of 2 qubit entangling gates, we have realized the Toric code ground state. And this actually scales very well with system size. So if we went to a bigger system size, this actually scales linearly with the shorter of the 2 depths. Okay, and this can be shown to be the optimal scaling for such a quantum circuit. Okay. Right, so now let's go back to this bigger plot. This is the final results for the ground state. So what we've done here is we've actually measured the expectation value of all of these star and plaquette operators and shown the numbers in the middle. So the average like stabilizer fidelity, so these star and plaquette operators are also called stabilizers in the context of surface codes. The average is about 92%. Okay, so this is actually very impressive that we can get such good numbers, and it's sweeping under the rug that this is not actually what you get when you just run the experiment. There are layers of error mitigation and some other clever stuff to analyze the data, but we can get very high fidelities for this Toric code ground state. Okay. So now we have this state, we're going to play a few games. We're going to extract some of the interesting features of this state and play with the anyons. So the first thing we want to do is look at what's called the topological entanglement entropy. So if we look at the entanglement entropy of a subsystem of just any ground state of a local Hamiltonian, then what we generically expect, although not proven in 2D, is that we have an area law. Okay, so we have that the entanglement entropy is proportional to L, which is the length of the cut. So if this circular region is our subsystem, then it's proportional to the length of the boundary. However, for topological systems, we have this additional constant, this minus gamma, which is a subleading constant term. Now the alpha in this linear part, this is a non-universal constant. This all depends on the microscopic details of the model we care about. However, this gamma, this is a universal constant. This is determined by the topological phase that we are in. In particular, as a detail, this is equal to the logarithm of the total quantum dimension of the topological ordered system. In our case, this is just equal to log 2 for the Toric code. So this gamma should be equal to log 2. And this quantifies something that can't be removed unless you go through a phase transition. And the way to see this is that we have this minus sign here. Okay, so we have a minus contribution here. So by scaling, by removing this area law part, we can't go into a product state without crossing a phase transition. Now, the way to actually extract this universal part is to cancel all of the non-universal parts. So there was a couple of papers, Kitaev and Preskill. There's also a paper by Xiaogang Wen that showed that you can partition your system into 3 parts, and by cleverly adding and subtracting the entanglement entropies, you're left just with this universal piece. Okay, and if you just look at this picture, A, B, C, these are your 3 partitions. You just add up in this way, you'll find that each of the boundaries appears equal number of times with positive and negative signs. So all of the boundaries in this picture will cancel, and all you'll be left with is this gamma. Okay, so that's the idea. So then we did this experimentally. Okay, or when I say we, I should say Google's experimental team did it, but here are the results. So we did this for 3 different sized partitions. So we used 4 qubits, 6 qubits, and 9 qubits, and these are the ways we split them up into A, B, and C. And now combining these, you have lots of different size subsystems. Okay, so for instance, this A in the top left is this guy here. If you combine A, B, and C, you'll end up with this square guy down here. You know, combine A and B in this 6 qubit picture, you'll end up with this guy in the middle. Yeah, I hope you can see my mouse, otherwise this probably doesn't make much sense. Okay, so then, because the Toric code is so simple, we actually know what each of these contributions should be. So this area law part, which is generally non-universal, we actually know what it is for the Toric code. And so for each of these partitions, we can actually check that we get the right value. So in this big figure on the bottom, this is what we did. We computed all of the possible partitions that we need to compute these, you know, this subtraction scheme, and we plot the value of the experiments here. Now, what we're showing are distributions, and the reason is because we can fit these 9 qubits, 4 qubits, 6 qubits in several ways on our 31 qubits, right? So, you know, we can select 4 qubits up here, 4 qubits down in the bottom left, 4 qubits in the middle. So we did all of these combinations, and we additionally considered all of the possible rotations. So, you know, if you look at the top left guy, you know, these are not rotationally symmetric, and so we can consider all of the possible rotations as well. And so what we end up with are these distributions. Okay, so the bottom right shows that all of the partitions, they give the correct values. So this matches the gray dashed line, which is the theoretical value for all of the system sizes. And now the amazing plot is really this middle green one. So this is when we do the subtraction scheme of all of these values, and we actually get very close to this value of minus log 2 for gamma. So on the top, we have this 2x2 system, 2x3, and then 3x3 on the bottom. Right, and you might notice that it's kind of getting better as we go to larger system sizes. Now, you could read a lot into this if you want, that maybe because we're going to larger systems, it should get better. But then this can be counteracted by noise. And so honestly, I'd say this is probably luck, but in all cases, we're getting very close to this value of minus log 2. And importantly, we checked what would happen if we just start with a product state. So if we don't do all of this complicated circuit to get the Toric code, just start with what you got, you find basically exactly 0. Okay, so we're definitely not in a product state is what is coming from this. We're definitely realizing this topological entanglement. Okay, so a detail of this is that for the 4 qubits and the 6 qubits, we just do brute force state tomography. Okay, so we just measure all of the possible Pauli strings for these qubits, and we reconstruct the density matrix and extract it from that. Now, when you go to 9 qubits, this becomes infeasible. Like, this would take ages, it'd take forever, and even then, like, the quality is probably not going to be very good because you have to reconstruct this density matrix. What we did instead is used a randomized measurement scheme. I should put a reference that was devised by Peter Zoller's group. Yeah, so essentially you measure in lots of random bases, and by using correlations of the statistics of your measurements, you can actually get the Renyi entropy, which is what we measured here. Okay. Great. So we've measured one thing, like we've shown that we don't have, a boring state. We have this topologically ordered state. But another interesting property of this model is that we have these anyons, these particle-like excitations that aren't bosons or fermions. And just to summarize, like, what characterizes these anyons, we have two things. We have first the exchange statistics. Now, this is something you should be familiar with from fermions and bosons, because this exchange statistic, swapping two identical particles, will give you plus or minus 1 for a fermion, or a boson, sorry. However, for anyons, this can take other values. So when we're in 2D, this is not restricted to just plus or minus 1. We can take other rational phases. Now, in addition to that, we also have something called the mutual statistics. This is not relevant when we're just talking about bosons and fermions in 3D. But when we're in 2D, if you have two distinguishable particles, then dragging one around the other can actually lead to a non-trivial phase as well. And that's called the mutual statistics. Now, these are commonly summarized in what's called the T matrix and the S matrix. Yeah, I just mentioned that. Okay. So how do we actually extract, how do we actually do this braiding experiment? Extracting this exchange statistics and this mutual statistics. Now, kind of schematically, what we do is we start with a pair of E excitations and a pair of M excitations. Now, it looks like we just have one. It turns out like the boundary can actually have a charge in this case. That's just a detail. But then we drag this E excitation in a full loop all the way around back to where it started so that it encloses M. Now, this is exactly the procedure that I'm talking about for the mutual statistics. Okay, so in doing this, what I end up in is exactly the same state I started with, right? So if you look at, forget the operators that are drawn here. So this X operator that's drawn as this red line, this is the operator I need to use to move myself. But the underlying like glass panel looks exactly the same. Okay, so we now have like the red means that the parity of this A is -1, so that's not what it should be for the ground state. And the yellow is a plaquette that has opposite sign. Right, so by doing this, we pick up, it turns out, a phase of -1. Okay, so the E and the M, the mutual statistics of these gives us -1. However, this is great, but we can't actually see this phase. Like, we know that a global phase is not measurable directly. Okay, so we've done this. We might have picked up a phase, but there's no way of knowing this. So what we have to do is use a kind of modified experiment that uses something called Ramsey interferometry, or in quantum computing terms, it's commonly referred to as the Hadamard test. Essentially, what we do is we add an ancilla qubit, which we put in the plus state, and now we do a controlled operation. So we essentially do this operation of moving E around M only if the ancilla is in state 1. And now by doing this, we actually put the phase into this ancilla qubit in a way that is measurable. So now by performing tomography just on this ancilla qubit, we can extract this phase, this e to the I theta, which tells us the statistics. Okay. Right. So this experiment up here, this would be quite ambitious to do if we're doing it in this controlled way. So what we do in reality is a little bit simpler. We start with configurations where the E and M are basically right next to each other, and we do kind of the minimal loop we can to extract this statistics. And now we have this ancilla qubit, which I show as a green cross off to the top right. And now we have a controlled operation that realizes this loop. So if this ancilla qubit is in the 0 state, we do nothing. If it's in the 1 state, we drag this E around the M. And by starting in like the plus state for this ancillar qubit, we end up able to extract this phase. Now, this top figure, this is the circuit we need to extract the mutual statistics between E and M. And this bottom figure that I show as just another example is the circuit we would need to extract the exchange statistics of the composite fermions. Okay, so by doing all the possible combinations, we can extract all of the mutual and all of the exchange statistics, and that's what is summarized on this right-hand panel. Okay, so the dashed gray line is the expected value, and the green dots, this is the data we actually extract from the experiment. Okay, so we have a bunch of them that are kind of trivial. These ones with the identity, these should all be 0. That's basically saying you move an electron around, you pick up no phase. We have the exchange statistics. So this says that the E and the M individually, they look like bosons. But then we have this combined fermion, which looks like, combined excitation, which looks like a fermion. Okay. Yeah, so this is just a way of us extracting this non-trivial statistics of these excitations in Google's experiment. Okay. So let me say a couple of words about how this system can be used as a surface code. And yeah, okay, so essentially, if we choose to draw our system like with a 45-degree rotation now, we end up with slightly different boundary conditions. And what this means is that we actually have a degenerate ground state now. And this, we have a twofold degeneracy associated with this boundary. And this actually allows us to store a quantum bit on this whole system. Okay, so essentially the way that you would measure this is by using now non-local string order parameters, this product of z's along horizontally, product of x vertically, to measure the value, the z value or the x value of the logical qubit, which is stored in this state. Yeah, I don't want to go into too much detail of how this works. You can look into it. But what we did was we came up with a simple circuit to realize this particular configuration, which is very similar to the one I showed before. We did it for a 5x5 case and a 3x3 case. So the idea is, as you increase the number of physical qubits, the error for your logical qubit, which is all of them, this should go down. Now, this is only true if the individual error rates of all of your gates is sufficiently low. Okay. So first thing we did is we just create particular logical states and we measure them. And because we just have a twofold degeneracy, this whole 5x5 system is really just a qubit now. So what we can do is plot all of these states on the block sphere. So we draw some of these main circles, and the data is shown by these data points. So you can see it's kind of, it reproduces this sphere, but it's all contracted inwards. So this is essentially an effect of the dephasing that happens over the course of this experiment and through the measurement error when we try to extract this. Okay. So now let's talk a bit about how you would use this for error correction. So getting a bit more into detail, like how you would actually measure the Z value, you would measure along this horizontal path, and you would take the parity essentially of this string. Okay. So it turns out you can also measure everything. Okay, and you know, because you're in the Toric ground state, that all of the plaquettes, all of the stars should be +1. So they should all be blue. And so if you measure and you find that actually 2 of these are not +1, they're -1, then this means that somewhere errors must have occurred in your measurement. And in this particular case, these errors occurred in a way that actually changed the logical value that you would measure. Okay, so now to correct this, you would do the minimal number of flips that would get you back to all blue in this picture. So just by applying the X operator on these 2 red circles, you get all of the star operators back to blue. And this actually flips the logical value back to +1, correcting the errors that happened in the device. Okay, and similarly for the X measurements, you do exactly the same kind of thing. Now, on the right, we have a whole load of data. Let me try focus your eye on some of it. So if you look at these kind of 3-pointed stars, now this is what would happen if you started in the 1 state and you left it for a certain amount of time. What is the probability that you make an error? Okay. So this, even if you wait for no time, you got something like a 10% error here. And this 3-star one, this is for the 3x3 system, the smaller system. And if we look at these red 5-star data points, we end up with like a 15% error. So basically, if you just don't correct anything, you just look at what you have, then the errors are accumulating. Because you have a bigger system, you've got more errors, and so you have more chance of making these errors, logical errors. However, now if we do this correction scheme after we've waited for a certain time, then we end up with these red triangles and these red pentagons. Okay, so they both come down to about 0.3% if we look at the 0 wait time. And interestingly, these pentagons, so the 5x5 system, are slightly lower than the 3x3 system. Now, this is really not that significant. Let's just say they're about the same. But what this means is we're really at the edge of this error correcting threshold. So we take a 3x3 system, we correct the errors, we get a certain error rate, which is say 0.03. Now we go to 5x5 system, correct it, we get an error rate which is the same. So this means that scaling up, the errors that we add by having a bigger system are pretty much exactly compensated by this topological protection now. So we're really at this cusp of error correction being useful. Okay. And just to point out, this is really a passive scheme. So I'm doing this, we put it on the system, we just wait, and then at the end of the experiment, we correct it. Now, what you really want to do for error correction is to be constantly correcting errors as you do your circuit on top. Okay, so that's an extra step. Okay, so I don't want to hold lunch up too long, so let's try to be a bit quick with this part. Essentially, the point is that the Toric code is the simplest example, but we've been able to generalize this so we could, in principle, realize a large class of topological models, which are called string map models. Okay, and the important thing is this allows us access to something called non-abelian anyons, which are potentially more useful than these abelian anyons that the Toric code has. Okay, so the first step is that we should move to the honeycomb lattice. So the square lattice works for the Toric code, but more generally, the square lattice isn't ideal. Essentially, we want this kind of trivalent vertex structure in our lattice. Okay, so we move to the hexagon, that's no problem. And then we can redo this just for the Toric code to start with, okay? So we have, again, the plaquette operators, but they would now be around the hexagons, and we have the star operators, which would now be around these three-pointed stars instead. Then we can have a gate sequence that acts exactly like we did before. So it's kind of got this sequential nature. We have a lot of gates put in parallel, and then we kind of sweep through the system. So I didn't really comment on that before, but that's why our circuit was so efficient, that we have this parallelization. And for the Toric code, basically all the gates we need are, again, these CNOT gates. So if I just quickly skip back, these are the CNOT gates that we're showing here. Okay, we can do them in parallel, so you have them in kind of this row-wise fashion, and then you sweep through your system. This follows over directly, essentially, to this hexagon lattice. But now what we can do is be more general. So rather than having these kind of hexagonal operators where we have all of these CNOTs, we have a slightly kind of dressed hexagonal operator, and this is no longer just simple CNOTs. Okay, so now this is some maybe quite complicated conditional operator, but the idea is the same. Essentially, we have these plaquette operators and star operators. They all commute, and what we want to do is to construct projectors onto these plaquettes. Okay. Yeah, you can look at the details in our paper, but the important thing I would say is that we can realize one of the simplest models for non-abelian anyons. This is the double Fibonacci model. Now, by braiding these anyons, this is actually capable of universal quantum computation. Now, you might realize how funny a statement that is, that we're using a quantum computer to generate anyons that you can braid to do universal quantum computation. But that's not really the point that we're making here. Like, we can realize really exotic topologically ordered phases on these quantum computers. Right. But then the final thing to think about is practicality. Like, can we actually do this on Google's computer now? And the answer to that, as you might expect from some of the previous talks, is no, not yet. So while we needed 5 layers of gates, 5 layers of 2-qubit entangling gates for the Toric code, to realize this more complicated model, we would need about 120. So this is, between an order and 2 orders of magnitude higher. Okay, so we need quantum computers that are an order or 2 orders of magnitude better before we can really reach this. Okay. So just as a kind of quick outlook on some of the things I mentioned, like the next step for this surface code stuff would be to actively correct the errors. And now this could be motivated by the passive experiments that we did. So it can kind of motivate how regularly you would have to actively correct to get reasonable errors. But our experiments already show that we're kind of on the cusp of this error correction. And so maybe, with the next generation of devices, we'll start seeing some experiments where active error correction has been implemented. And I think there have been some recent experiments also by Google that have demonstrated this on very, very small systems, but have demonstrated this principle. Yeah, and then the next step for this generalization is to actually try to realize some of these more complicated string net models. And then once we have these, so I didn't really mention this, but these are exact states that we know how to simulate, how to construct, but these can act as important starting points that we can build on top of. Just like the Laughlin wave function is an exactly solvable description of quantum Hall, like it's still a useful starting point for more realistic systems. Okay, and yeah, I'll just leave this slide up for you to see. Thank you very much for your attention.
Yeah, thanks for the very interesting talk again. Any questions?
Sorry, I don't hear anything at the moment. I don't know if I should.
Yeah. Can you hear us?
I can hear you now. Now it's silence.
Now, can you now?
Yeah, sorry, it was breaking up. I can't hear what you're saying.
And now can you hear me?
Yes, now I can hear you perfectly.
Okay, good. Still, you can still hear me?
Yes.
Okay. So I'm completely new to this field, so my question is maybe stupid for you. But, so the surface code is definitely adapted to 2D superconducting devices, I guess. Are there any equivalent for other type of architecture for quantum computing?
Yes. So this particular version that I'm showing here is designed for the square lattice, and Google's devices really were designed with this in mind. So this connectivity of Google's devices was really designed for this purpose. Now, if you look at IBM's devices, they also have error correction in mind, but they chose a different route. They have used something called a heavy hexagon lattice. So it's like this hexagon lattice, but you have spins on the bonds as well as on the sites. Okay, so both of these have the toric code, surface code in mind, but they've chosen different routes to realize this.
Okay, so depending on the startup and on the architecture, it will always be different, and we cannot use a code. I mean, for a software point of view, can we use a code from Google for an IBM machine or not at all?
I think it's more the other way around. Like, people are designing their chips based on what their plan is, and they plan to implement the toric code to do error correction in a particular way, and that is what has motivated the design of their chips.
Okay, thank you.
Sorry, can you hear this microphone as well?
Yes, I can.
Okay. Any other questions?
So, yeah,
Sorry, it's gone very crackly again.
Okay, sorry, can you hear me?
Yes, I can hear you.
Okay, great. So I said nice results. So as you also said towards the end, these states can be described classically in an exact way, right? So in a sense, we can claim that also on a classical computer, we have topological entanglement, because I mean, I can just measure it out of my wave function classically. So so the question that I want to make you is concerning the perspective of this, right? So what do you see that as an interesting perspective that could go beyond indeed what we can simulate classical?
Okay, so there's a couple of things there. So the reason why these are solvable is because of these commuting projectors. So it's really that we can solve this by hand. I can just, you know, count to get these values for the entanglement, for instance. However, if you really just do, like, you're a bit more ignorant about this, you just put it on a classical computer as a tensor network or something like this. Well, there's also PETs that do this more efficiently, but generally, this is actually going to be a bit of a problem. You do have 2D area law entanglement. And so if your system size gets big enough, this will limit your simulations. Okay, so that's just the first comment. The comment about, you know, what could you actually usefully do, like along these directions? There are proposals to use this kind of background toric code to realize statistics of particles. Okay, so as you've probably heard, there are ways of using like Jordan-Wigner or Bravi-Kitaev to map from fermions to qubits. You can actually use this combined excitation in this model. If you have a toric code background and you have your fermions on top coupled to these fermionic excitations, you can actually have a local way of realizing fermionic statistics. Okay, and then this allows you to go to complicated interacting models of fermions. So that might be one practical application of this.
Yeah, that's really so. Just a comment on the first thing. You can realize essentially all these states exactly with neural networks. So beyond the facts. Okay. But anyways, no, just to say it's not true that you cannot simulate this class.
No, true. And like, yeah, you can write it by hand. So again, like it's
the second application, yes, very interesting.
Yeah, and one extra thing on there is you can use this as a starting point, right? If you take this circuit and you apply a finite depth quantum circuit to it, you can generate potentially a lot of entanglement, go away from what is classically simulable, but you will still be in the toric code phase because you've applied the finite depth quantum circuit. So it gives you a solvable reference point that you can move away from in a controlled way.
Any other questions? I have a quick question. Can you hear me?
Yes, I can.
Sorry. I asked you this question many times, but no, when you showed the 3 and 5, the graph, but how would it look if you just have one qubit? How would it compare?
Just one qubit. Okay.
Yeah,
so,
just the qubit itself. Yeah.
So if you have one qubit, so actually the error rate is about 3%.
Sure.
So that basically all three of them, if you wait no time, you just construct it and you measure it, then 1 qubit, 9 qubits, 25 qubits, they're all giving you the same effective error rate with correction. So this is basically saying that the error from going bigger versus the error protection exactly canceling.
Okay. Okay, interesting. And here you show that 3 and 5 gives essentially the same, but there was this other paper by Google where they have they did a they have a distance, and then they show when you go for the distance from, I think it was also 3 to 5 or something like that, and it was getting worse in that case.
Yeah, so I don't remember exactly, but I think this is maybe an older paper that you're referring to, and I don't think they're using the toric code. They're using a different. They're using a different error correcting code where you have a different distance.
Yes.
So yeah, there's different things there. So different error correcting codes will have different thresholds. That's the first thing. Mm-hmm. The experiments get better over time. Even the same physical chip, they can improve with software and other things. So, you know, the fact that they're exactly coinciding, I'd say, was probably luck. And it's just the signature that we're close to this threshold. And by going an order of magnitude further, we might be in the error correcting regime.
Okay, thanks. Unless there are other questions, let's thank again the speaker.
Thank you.
And just before I maybe hand over some final comments, let me just thank the organizers briefly, because it was a great conference.